All right, so we're going to do another related rate problem. And again, before we go through and make a list of our information, we need to draw a picture of what this looks like. So what we have is we have a cylinder, and at the top of the cylinder is the piston. So imagine the piston's all inside here right now. Now what's happening is this piston is moving down the chamber, all right? So what we are ending up looking for is we are looking for what happens when the piston is exactly 2 centimeters from the base. All right, so we will start with what we have that is given, and I already have written some of that down. But what we know that the radius of this cylinder is 5 centimeters, and that is given to us right here. In order for us to decide what rate this is, it's important for us to look at what the cylinder itself. We're talking about the fact that we have the volume of a cylinder, and the volume of a cylinder is part of our known information, and it is pi r squared times the height. And what's happening is we have the initial height from the top of the cylinder to where the piston starts, and that height is changing. And as I said before, this height is changing at this constant speed of 3 centimeters per second. So that's what we're looking at. So part of our given information here is that dH, the height of the piston over a given time, is changing at 3 centimeters. And because this is a piston that is going down, this must be a negative 3 centimeters per second. So what we are trying to find in this case is the rate of change to the volume. So we are trying to find dV dt, and we know that happens when the height of the piston is at 2 centimeters. So to start with this, we're going to again start with our known piece of information and take the derivative with respect to time of our known information. When we do that, we get dV over dt is equal to pi dr dt times 2r times dh dt, and the derivative of h is just 1. But if you look at this dr, we don't have any information about dr, but even more than that, we are given what r is. So let's go ahead and back this up. We don't have any of this information. We don't have dr dt, but we do know what the whole radius is. So if we did this, it's not going to get us anywhere. We want to go ahead and take a step back and not do this. We want to go back. And the reason I showed you that is I want you to see sometimes don't just dive right on into your known equation. Sometimes it's better to start. I know that the volume is equal to pi. The radius in this case is constant, and it's a constant 5 centimeters. And that's really nice because now this changes it to 25 pi centimeters squared times the height. Now you can go through and finish doing this. Again, take d dt of both sides, and then you're left with dv of dt is equal to 25 pi centimeters. That's a constant, that doesn't change. And then the derivative of h with respect to time is just dh over dt, and the derivative of h is just 1. We know, based upon our given information, that the derivative of h with respect to t is 3 centimeters per second. So now we're done. And we can just say all of this is equal to 25 pi centimeters times 3 centimeters per second, because again, that 3 centimeters per second is getting replaced with dh dt. And all of this is equal to minus 75 pi centimeters per second.